This is Jason with Liquid Instruments. Today I'm going to show you how to implement a custom matched filter using the Moku FIR Filter Builder. We'll be working in multi-instrument mode today, so after connecting to your Moku device, click the appropriate icon. In this example, we're going to put the arbitrary waveform generator in slot 1 and the FIR Filter Builder in slot 2. The connection map is quite simple in this one, so just click Apply Changes and wait for the FPGA to configure. So let's open the menu of the arbitrary waveform generator first. So what we're going to do here is set up the AWG to generate a chirped pulse, like something you'd see in a typical radar application. Let's set the repetition rate to 200 Hz and the peak-to-peak voltage to be 1 volt. We're going to use the equation editor to calculate our chirped waveform. Set that on the right and double-click on the plot to pull up the equation editor. And the equation of our waveform is cosine pi times 200 times t squared. So the frequency will get larger as t gets larger. Let's click Save and check that our chirp looks good. Now go over to the menu on the right and let's set it to pulsed mode and enable the output if it's off. So now we're generating a chirped waveform. Let's head over to the FIR Filter Builder. We're going to enable the embedded oscilloscope by clicking this icon in the bottom right. And we're going to place probe A near the output and probe B near the input so we can see the change before and after the filter. So the output is disabled for right now, so let's just look at the before signal. We can see our chirp pulse being recorded going into the filter box. We're going to implement something called pulse compression. So we're going to design a custom matched filter, one that matches the shape of the waveform reversed in time. So click on the filter in the center, and we're going to open the Impulse Step Response tab. We're going to make sure the design domain is in time, and that the window function is set to none. And the shape of the impulse response will be determined with an equation. Now we click on our equation editor again. The equation is almost exactly the same as our waveform, except instead of t squared, we've replaced it with 1 minus t squared to reverse it in time. So click Save. Now, it's important that the time domain impulse response of the filter is the same length as the pulse itself, which is 5 milliseconds in this case. I've already adjusted the number of coefficients and the sample rate to take this into account. So now let's click out of this and let's enable the filter. And let's auto scale. Now we see a spike on trace A. This is a result of the pulse compression. The waveform, after going through the filter, is shortened in the time domain and thus has a higher peak power and signal-to-noise ratio. Now this is useful to determine the time of arrival. If you have multiple pulses overlapping in time, then this filter can separate them out temporally. And it's also useful for recovering a known pulse shape from a noisy background. So let me show you that really quickly. If we return to the AWG screen, I can go over to the right and I can change this to custom. So I've uploaded a custom waveform, which is an identical chirp, but with some random noise injected into it. It looks barely recognizable to the naked eye, but if we put it into our matched filter, as we can see on the oscilloscope, we see that the pulse compression works just as well. And it's easily picking out this pulse among the noisy signal. So we've implemented a custom matched filter using an equation, and that'll be all for today. Please subscribe and check out liquidinstruments.com for more information.